Ngày bớt
Good morning, sir. इधर है नीचे इधर लाइब्रेरी में जा लाइब्रेरी कौन सी है? Sir, please unmute your mic.
Yeah, good morning, Professor Garg and others.
Yes, sir. Sir, please 2 minutes at least participants are joining. So please, we'll take maximum 5 minutes, sir. We'll start this session.
No issues, no issues.
Yes,
yeah,
sir.
good morning, Dr. Sab.
Good morning, sir.
How are you, sir? RK Garg.
Yeah, yes, Professor Garg. Thank you, sir. Thank you. I am here. So let us wait for another 5 minutes.
I was just discussing with Dr. Pradeep that early in the morning at about 6 o'clock, I sent a WhatsApp message to all the experts for 2 days. But immediately I got a reply from you. So I was telling
yes, sir,
that.
Yes, sir. Thank you. Thanks for reminding me. Thanks for reminding me.
At about 6 o'clock in the morning. मैंने disturb तो नहीं किया sir आपको?
No, sir. That is my schedule. Thank you.
और
Thank you, sir. Thank you.
जम्मू में?
बस सर इधर आज धूप अच्छी है, उधर पता नहीं, इधर धूप बहुत अच्छी है आज. The sun is good today. So nice seeing that a lot of participants have joined.
Yes, sir.
I can see
around 40 participants have joined, sir.
Great. And that too on time. They're almost on time. So this is good. People are, getting interested in 3D printing and other things. So it's my pleasure sharing my experience. So we'll just start after 5 minutes.
Yes, sir. Yeah, definitely.
Yes, sir.
अच्छा मैं ऑनलाइन मैडम डाक दे रहा हूँ ऑनलाइन मैडम डाक दे 5:30 मैडम 5:30 तक हैं काय कोण मैडम अपना उठी ना आली वो एते समय देखिली काम में तो उठी जाए वो नॉन मैडम के लगी छे
भुई असला ना नाही
A very good morning to one and all. Hope you people are enjoying the FDP and acquiring the knowledge in the field of 3D printing from the last 3 days. So let's start this beautiful morning with the thanking of gods and warm welcome to all the dear participants. I welcome you all on the behalf of Department of Mechanical Engineering, Deen Bandhu Choturam, University of Science and Technology, Murthal, on the 4th day of 1 week ATAL Faculty Development Program. Today's sessions will be on various topics like 3D printing, polymeric parts, mechanical and tribological applications, metrological assessment of additive manufacturing parts, and 3D design of ankle foot orthosis and concepts of additive manufacturing by the different eminent speakers as per our schedules. The various speakers of this eminent speaker of our schedules for today are Dr. Irfan, Dr. Harish Kumar, and Dr. Kasim Murtaza. So let's start our first session of the day with our eminent speaker, Professor Dr. Irfan, who will deliver a talk on 3D printing, polymeric parts, mechanical and tribological applications. I welcome Dr. Irfan on this 1 week ATAL Faculty Development Program. Welcome you, sir. So Dr. Irfan, as currently working as Assistant Professor at the School of Mechanical Engineering, Sri Mata Vaishno Devi University. He has previously worked with the R&D wing of Mahindra & Mahindra. He has obtained a Bachelor of Technology in Mechanical Engineering from SMVDU University and Master of Engineering in Mechanical System Design, a gold medalist from National Institute of Technology, Srinagar. He has carried his PhD in the area of tribology at SMVDU University. He actively involved in teaching and research for the past 7 years in the fields of material, tribology, and 3D printing. His research interests include lightweight materials, new product development, and 3D printing, development of green lubricants, self-lubricating materials, and cutting fluids, mechanical testing of composites, frictions and wear of materials, surface engineering. He has published around 25 research papers in SCI and Scopus Index Journal. Moreover, he has been awarded various research grants for various projects from various agencies like DST and NPIU AICT. He has attended numerous conferences and workshops both in India and abroad like USA and Singapore. He is a number of reviewers boards of various international journals apart from chairing technical session in various international and national conference. Dr. Irfan is actively involved in organizing various conferences and workshops. He has also coordinated various student events such as SAE Baha, Eco Cards, and TEDx. Moreover, he has supervised around 6 masters and 12 bachelor level projects. So we welcome you, Professor Irfan. Thank you for being with us for today and making this program successful. Thank you very much, sir, and we welcome you all.
Thank you, sir. Thank you, sir, for this introduction. But I am a very small person working in a small lab. So with all the little facility we have been working along with my students for the past 6 to 7 years in the area of 3D printing. And I will be my talk will be little bit inspiring to those faculty who don't have research facilities at their labs and they want to do something. So that would be the key takeaway from my, you can see we don't have any facility in our small colleges and we want to work. So I hope that my lecture will be little bit inspiring in that direction. So I thank Professor Garg and the co-organizers from Dinbandhu Choturam University Science and Technology for giving me an opportunity to talk on 3D printed polymeric parts, mechanical and tribological applications. So this presentation may contain some uncited content which belongs to their respective IP owners, and here we are being this is being used only for educational purposes. And part of this presentation also includes research work of our group, which is either unpublished or under review or work in progress. So I'll be discussing some details about basics of 3D printing, some application areas, and some basics I'll be touching of tribology, and directly we will go with some research results and discussion about mechanical performance of 3D printed polymers. And then in the second part, we will discuss some tribological behavior of 3D printed polymers. And then I will discuss and share with you some case studies and projects which we have done in our lab here. So that is the overall outline of my presentation. I hope the speakers who have spoken before me, and I have seen the list, they are much experienced and learned than me. They must have touched the various other aspects of 3D printing. So if you see, the basic of 3D printing is, you start from a CAD file, and then the software converts it into an STL format, and then layer by layer the part is developed, in contrast to the subtractive manufacturing, wherein we start from a building block and then we do machining or cutting. So it is that is why we call it as an additive process, and the part is developed layer by layer according to the data stored in the STL format. So the question comes, why we should do away with the conventional processes and start with 3D printing. The kind of flexibility that 3D printing gives in developing complex parts. Imagine this geometry, which is a lattice structure, and developing this by some cutting operation would be very difficult. It is almost impossible. But through 3D printing, it is possible, as well as the complexity is free. A lot of material saving, because when we start from the material like this and do subtractive manufacturing, there is a lot of waste which gets produced. So that is an unsustainable way. And the speed and the part quantity with which 3D printing can develop products is remarkable and much better as compared to the conventional processes. So as I told, that additive manufacturing, we get the complexity for free. So this graph basically shows that if we add complexity in our design, because we always, want that the geometry is optimized, very complex structures are being developed with the advent of computer-aided engineering. So, but ultimately where we used to get stuck is how to manufacture that part. And a very good application is, suppose in the case of cooling channels. So it is very difficult to drill very intricate and complex and very curved holes inside parts, machine tools, where we want the lubricant or the coolant to flow. So, but additive manufacturing has made it possible, and that too with no additional cost. So there are various types. I think you are well versed with these different types of 3D printing, like the powder-based selective laser sintering, wherein powder is used as a starting material, and a laser selectively sinters each layer of powder, and depending upon the movement of the laser, the powder is sintered.
Excuse me, sir. Sorry to interrupt you. Sir, please, I think, share your screen. Your slide is not visible. I thought initially that you are giving some introduction, but I think so.
Oh, you should have told me earlier. I thought.
I thought, sir, it's a brief starting introduction. That's why I did.
Okay. No issues. No issues. I'll just go. I'll just go through the slide. Now it is visible.
Yes, visible, sir. I'm sorry, sir.
This was the first slide. So just I will go through these slides quickly. So I talked about this disclaimer from my side. This is the outline I was talking about. Then I talked about what about basics. I was talking about why 3D printing. So then I was talking about part complexity, that complexity is free. And this graph shows how, additive manufacturing enables us to manufacture products, complex products, and that too at a very low cost and with no additional cost. So I was discussing about the types of this additive manufacturing processes, wherein we were discussing that there are mainly three types of base materials. One is a powder, second is liquid, and third is solid. And in case of powder bed, we use a powder as the base material and the laser sinters selectively. That is why we call it as a selective laser sintering. Likewise, in liquid based, we have fused deposition modeling, which is not a liquid based, but it's a semi-liquid based, wherein the starting material is basically solid, but later on, because of the extrusion and heating of that polymeric material, the material comes out in semi-liquid state. Likewise, stereolithography and laminated object manufacturing, but my discussion would be more on fused deposition modeling. So that is why I will discuss with you how this fused deposition modeling method works. In this, we have, if you can see this coil. So this is the starting material, and this is fed through a driver motor inside an extruder. The extruder actually heats this material, and there's a nozzle. It comes in different diameters. That nozzle, this material comes out through this nozzle in a semi-liquid state. This extruder is free to move in all directions, X, Y, and Z. And depending upon the information stored in the STL format of each layer, the extruder moves in different directions. So say, for example, we have to print this cup. Initially, the extruder will move in a circular, will form the first lamella of this. Later on, since we have to print this handle also, so it will drop some material here. So that likewise, layer by layer, the material will be deposited, and it will get bonded to the previously deposited layer. So I have one video on this. I will share with you at the end how a 3D printer works. If you want a hands-on experience and have a touch and feel of how it works. So different starting materials are basically used, but in case of this fused deposition material, fused deposition method, it is compatible. It is compatible for polymeric materials only, because to heat metal and to make it in semi-liquid, it is not that easy. That is why in case of metallic additive manufacturing, we use powder as the starting material, and then sinter it selectively by the laser. So these are the materials which are compatible to FDM, ABS, polymer, acrylics. So these are all available materials which come in spools, and a new class of materials which is now available is some composite or nano composite fillers, or these spools are also available, which are basically polymeric composites or polymeric nano composites. So directly you can feed the 3D printer by that spool, and directly you can print a material made up of polymeric nano composite or a polymeric composite. So a lot of material options in case of FDM also, and given the vast application of polymeric materials in primarily in automobile, in furniture applications, decking applications. So a lot of things can be done in this area if we have an FDM printer with us. Typically, the various parameters which we can vary and which affect basically the part quality or the mechanical properties of a 3D printed part. We have divided them into four categories. One is the machine. Second is the how you orient the part. Third is the working parameter and environmental factors. The machine, you can vary the bed temperature. Bed temperature is temperature of this bed, where the base plate is there, because once you drop the semi-liquid molten polymer on this base plate, if it is too cool, it will get, there will be a thermal stress which will get developed in the polymeric material. So that is why we keep it little bit at an elevated temperature, so that when it so that the material is not getting too brittle, or it is not getting solidified too fast. So and that actually ensures the better bonding between subsequent layers. So model build temperature, what is the temperature of the model, and the machine calibration, what is the diameter of the nozzle. If you want to say, for example, print very fine geometries, so then a smaller dia nozzle would be helpful. And if you want to print, say, for example, some advanced or some composite material, so then the nozzle material also matters. Which material is it? Then part orientation. If, say, for example, we have to print a cup, part like this, say, for example, this. So there are four orientations in which this part can be printed. So we can start from here and end here. Another way is to put it laterally and then print it. So depending upon the part to be printed, we have to actually choose the part orientation, how I will start printing it. Then working parameters, raster angle, feed rate, infill pattern, raster width, I will discuss in next slide. Then environmental factors also. We have seen then when the fan or AC in the lab was on, and if it was off, so there is a warpage which happens. So the ambient conditions also matter while determining the quality of the part, and which will ultimately affect the mechanical property. This is basically effect of layer thickness. If you increase the layer thickness, you will see that a part which is printed would be rough like this. But if you want a smoother and you want to capture the geometry very perfectly, then you have to decrease the layer thickness. So this is how a small variation in the I would say layer thickness will actually vary the part quality. So we were talking about in our previous slide about different patterns. These are different infill patterns, how your material will be, deposited. So this actually helps in weight saving also. And honeycomb structure, triangular, rectilinear. We have tried some of these in our work also. And infill density. So infill density, say for example, 100% infill density, 70% infill density. Part orientation, what I was talking about, how you build this part, layer thickness, what would be the thickness of each layer while you print it. So the other parameters, like we were talking about raster angle, when it prints, how it prints, like this or this, what is the angle which it makes? So what is the number of contours which it keeps in each layer at the periphery? So these all parameters actually, determine the mechanical strength of these 3D printed parts. There are some challenges also. Say, for example, in a typical FDM process, there is a cold layer on which a hot layer actually is deposited. And because of this differential temperature, I would say temperature gradient. There's a stress which gets developed, and that actually leads to contraction and may lead to warpage. That is why we have to choose an optimal bed temperature and optimal, extruder temperature also, so that the temperature gradient is not that much, and the bonding is perfect. The bonding of interbonding, I would say the interbonding strength will actually determine the quality of your part, be it mechanical strength or any other property. There are, if you say, if we take 3D printing in toto, so there are some, challenges which need further research and further improvement. Say, for example, we have limited choice of materials, particularly in case of metallic 3D printing, and the cost of materials is not that low, and dimensional accuracy, because of these warpage and other things, we are not getting that, I would say, accurate dimensional parts. And mechanical properties are also not that good, depending upon the process and the parameters. So, and lack of standardization, because not much work has been done yet. So you cannot say that, say for example, if there is a material and you want to get a part which is good in tensile strength, what should be the printing parameters? Because there are papers, lot of papers which are published, but still there are not standards which are available so that we can replicate the same and get good results. And if you talk about cost, the fixed cost, you can see that in case of your conventional or traditional manufacturing, the cost is high in all the cases, while as in case of 3D printing, it is low. Be it supply chain cost, be it tooling cost, setup cost, it is low. And you could purchase, as on date, you can purchase a FDM printer as low as 17,000. So you can have a printer at your home and in your lab, and you could start, printing small samples or small products. We all know sustainability is the buzzword, and yes, 3D printing is sustainable because less waste is produced. We don't require any specialized tools or fixtures for additive manufacturing, and it has actually ability to develop lightweight parts, because whenever parts will be lightweight, they will actually help in fuel saving and reducing the carbon footprint, so that actually will lead to sustainability. And largely all these additive manufacturing or 3D printed processes, they are material efficient when we compare them with traditional machining and casting. So as I discussed, that it has the ability to produce optimized geometries. When we talk about optimized geometries, it would actually, develop products which are good, which are having good strength to weight ratio, and ultimately we will have lighter and efficient engineering products. And it has the ability to create on-demand spare parts, reducing or eliminating inventory. So we no longer require an inventory. If we have the geometry or the CAD file of a spare part, we can develop it, provided we know that it is not, the intellectual property is not protected. So we can develop, or we can even, say, for example, in case of very heavy machinery, or say, for example, in case of a turbine blade, if the turbine blade is worn out due to erosive wear, we can apply additively some material at the places where the wear has happened, and eliminate the complete replacement of a turbine blade just by depositing material by means of additive manufacturing at that particular point or at that particular feature. Things could be very sustainable and cost effective also. So if we talk about application areas. The application areas, you imagine any industry or any field, 3D printing will have a role to play or is playing a role. Particularly in case of medical and aerospace, I would say that 3D printing will actually revolutionize the things, because there we have complex designs, and we want them to be lightweight, as well as we want the designs to be optimized, and 3D printing will actually play a role in it. So these are the different application areas where 3D printing finds applications: medical, aerospace, electronics. Then we have this spare parts in case of automotive. So automotive, a lot of applications are there, and medical, I would say, and that too post-COVID. So if you see the market size of 3D printing, primarily 3D printing, if you remember, we used to call it rapid prototyping. So rapid prototyping, it no longer is known by that name, because now functional parts are being developed by 3D printing. And if you see the market size, that market size of functional part manufacturing is growing, and it is anticipated by 2024 it would be around 33%, if you see. And if you see the country wise and the rest of the world, if you see in USA and other countries, how the market share is increasing. So that is the future. And future is basically your old toothbrush. You find that in the night that my toothbrush is getting old, you will give a command to the printer, and tomorrow morning you will have a customized toothbrush, and you will use it in the morning. So that is the future. And I actually have put some slides related to this product design, because the title of the FDP was 3D printing and product design. So if we talk about 3D, this product design, it is, or the design process, it is a process from art to part. We have ideas, and then from those ideas, we do some feasibility analysis. Then after that, we have prototyping and the final production. How 3D printing will play a part in this, I will try to discuss. So we all know that the design environment has changed. The old design process was very slow, and the product development cycles were not that shortened. Today, we see the life cycle of a product is very less, and design time for each product is getting shortened. So in that, 3D printing will actually play a part, because apart from prototyping, developing parts directly, because it does not require any tooling, it does not require any separate fixtures or any dies or any like we have in case of casting or any other things. So we don't require any molds or any other secondary manufacturing, I would say, infrastructure. All we require is the CAD files. So if we see, if we compare the old design process and the new design process, things have completely changed. We need frequent design improvements, and the communication is very fast with the end users. We need to change, and we need to keep the customers satisfied. Otherwise, we are out of the market. So that is where 3D printing will come to the rescue of the industries, or to the engineering fraternity. If you see how 3D printing in design, if you see from prototyping to design iterations, including part complexity in a product, in topology optimization, introducing new materials, benchmarking, design for sustainability, design for assembly, these all pillars or the facets of some of them are related to life cycle engineering. Some of them are the steps in a product development cycle. They all will actually help in improvement in the manufacturing process. So we have to basically augment the concurrent engineering with 3D printing, and that will actually improve the manufacturing environment. One more important aspect of any design is, any design is somewhere a natural system is conceived by some person, and then we try to mimic that. And we cannot, because we all believe that nature is perfect. We cannot reach that perfection, but we try as engineers or as designers to somehow reach that. But these natural systems are complex. So mimicking those systems and developing those systems by conventional processes was difficult. But 3D printing, because we know the complexity is for free, and a lot of research is going on, and we have also started some work in this direction, wherein some natural system, we take lessons from a natural system and try to incorporate in our design, and then see that the product performance is improved. There are some works done by designing armor for defense application by mimicking fish scales, and the armor was designed developed by 3D printing. Plant tissue inspired furniture, wherein a typical lattice structure was developed, and then insect wing inspired lattice for shoe soles. And by virtue of 3D printing, we could develop 3D printing gun, which would actually, I request the participants to kindly mute. So
Sir, please unmute yourself.
Yeah. So these are the applications which were actually impossible by conventional processes, and 3D printing made it possible. So this is actually 3D printing meets biomimicry, and biomimicry in design. You can see in this diagram how 3D printing various methods can actually help in mimicking these natural systems, which are at the outer circle. And you can see the application areas in mechanics, in optics, electrics. So that is the beauty of this 3D printing, that you can, which were impossible to imbibe in your design, now it is possible. So looking at nature is now, I would say, easier, and developing products which are closer to nature would be easier. So what designers basically need is that any idea or any business is innovation driven. We want that the product development cycle should be short. It needs capital, and there is always, when we talk about entrepreneurship, there is always huge risk, and we are dependent upon manpower. But in case you use this 3D printing, I think everything will be reduced, be it shortening of this product development time, decreasing your capital cost. Risk is also less, because and then including this manpower requirement will also be lessened by using this. So again, prototyping, I will skip this slide, how prototyping helps in improving the design process, because it helps in design thinking, communicating, predicting the performance, checking the compatibility, simplification of design, and controlling various parameters beforehand, before actually printing or before actually manufacturing the product by any conventional process. 3D printing can help. So these are the things which we as designers or industrialists want. We want less material to be included. We want less initial investment, less labor cost, easy. So these all things will be, done by 3D printing. Now, another aspect is benchmarking. Whenever we are into product development, we are actually first study other designs. So designing is not like we will sit in a room and start thinking, and we may end up somewhere reinventing the wheel. That should not happen. Before we start any product development, we study previous art, we study competitors' products, we study the patents, literature. So that all has to be studied. But sometimes we don't have the designs. We have the product, but we want to analyze the products of a competitor or any existing product. For that, we need reverse engineering, and 3D printing can help in developing parts fast by benchmarking other products, or by doing reverse engineering of products, wherein, say, for example, the designs are not available, or they are protected by intellectual property rights, and we want to just study it. So their 3D printing will also play a part in the design process. So since part of my talk will be related to tribology, to those who are not from the field, who have not worked in the area of tribology actually was reported or coined by Peter Jost in the year 1966 in the famous Jost report, in which he concluded that if we use good tribological practices, the GDP of any global nation can be improved by 1%. So it is the science concerning friction, wear, and lubrication, and we know that 1/3 of the world's energy resources in present use appear as friction in one form or the other. So that is where we as tribologists, or we as mechanical engineers, are into picture, that we want to reduce the friction. Say, for example, in an automobile car, if the friction is reduced, there will be saving of fuel, and that will actually improve the lives of the people, number one, economically. Secondly, that will actually help from environmental point of view also. So there are actually what is tribology? Two surfaces coming into contact, and they are sliding on each other. There's a friction force which gets developed, and because of this, there is a lot of complexity which comes into play. There is chemistry, there is third body abrasion, various types of wear, how this wear happens, what is the speed at which they are sliding, what is the load, what is the temperature, what is the direction of sliding. These all things actually determine what is the coefficient of friction and how things wear out. So that would be discussed in one or two projects which we have done. So when we talk about wear and friction, it is not always that we want to minimize friction and minimize wear. No, it is sometimes the other way around also, depending upon the application. Suppose we are working for developing brakes, we are developing clutches, we are working on tires, on developing shoes. So we want that the material should wear out very less. That means it should have wear resistance, good wear resistance, or the wear should be minimum and friction should be maximum. So that is this application. And sometimes we want that it should have maximum wear, maximum friction, say, for example, in case of an eraser. And sometimes we want minimum friction, maximum wear, say, for example, in case of a pencil. And sometimes we want both to be minimum, say, for example, in case of bearings, gears, cams, sliding ways. So that means the area of tribology is very vast, and we have very different challenges depending upon the application. So I was searching I think some months back, I have developed this diagram wherein we could see that a lot of research currently is being done in the area of 3D printing with these mechanical properties into consideration. If we see the tensile property is being researched the maximum, and we could see a good amount of papers in tribology also that people are now studying the friction and wear behavior of these 3D printed parts. Now, I'll start with the work, what we have done previously. This was the brief background because I anticipate that the participants would be from different fields of research and different backgrounds. So that's why I thought that I will give a brief introduction so that you can connect with what I want to share. So the first project was basically on mechanical behavior of 3D printed parts, wherein we developed samples of polylactic acid, and then according to ASTM standards, and we varied the various 3D printing parameters such as primary layer thickness, bed temperature, infill pattern, and then we did tensile testing as well as flexural testing for these PLA samples. So honeycomb is another area which is very, if you see the honeycomb structure, it is again a biomimetic thing wherein we mimic the honeycomb structure in various designs, particularly it's good for, you can see here how the tensile strength varies with infill pattern. Here we can see that the triangular infill pattern is giving good results. Again, we could see that the bed temperature has an effect on the tensile strength. So if you vary the tensile strength for different infill patterns, the results are different. So likewise, for the flexural strength, we could see that a triangular pattern is giving good results. And if we vary the bed temperature in case of grid, the flexural strength improves, while as in the other two, the triangular and honeycomb, it is doing the other way around. Beyond 60 degrees Celsius, the flexural strength decreases. We have included in this work some good observations wherein we could see that the weight of the samples with different infill patterns. So if you see the honeycomb is giving the minimum weight, and the strength to weight ratio with different infill patterns, honeycomb is smarter than other two, and it is giving good results as far as the strength to weight ratio is concerned. We did some SEM analysis in which we could observe that there are differences in the modes of fracture which are happening, and primarily the interbonding strength is the key parameter which actually determines the strength of the part. And sometimes it was a brittle fracture, sometimes it was a ductile fracture, some amount of necking was observed prior to the actual breaking of the samples. So the key point which we found from this SEM analysis was that if the interbonding strength is improved somehow, the parts will actually improve the strength. So because the cracks and other things actually get initiated at the interbonding layer. So if that bonding is strong, the crack initiation may be delayed. Another small work which we did in this was related to 3D printed composites. It was related to PETG, wherein we introduced carbon fiber pellets inside these PETG samples, and then we tested it for tensile strength as well as flexural strength, and then in a separate work we have actually done the tribological testing of these samples also. So we could see that in case of PETG, we varied this infill density. If you see 40%, 70%, and 100%, and this is grid, triangular, and full honeycomb. And these results are for carbon fiber reinforced PETG, and we could see that the addition of carbon fiber as reinforcement, 20% by weight to the PETG, improved the tensile strength. So that was one result. And another important observation which we found, that at the layer thickness 0.1 and at all infill percentages, this behavior was observed, but not at higher layer thicknesses because of poor matrix and filler addition. And we could see a very good improvement in the tensile strength, which is around 114% for 40% infill percentage. And in the fracture modes, we could see that different fracture modes were observed. Say, for example, in case of the non-reinforced, we could see brittle fracture, while as in these images, the fracture was ductile, and the carbon in reinforcement, at lower layer thicknesses actually helped in improving the interbonding strength. But at higher percentages, we could see at the higher layer thicknesses, because of poor matrix and filler addition, that actually the trend was reversed. In case of bending strength also, we could see that the carbon fiber addition also improves the bending strength. And we could see from these images that how the crack propagated and how it is following those interbonding regions. The crack is propagating through those regions. So if the bonding is good, your fracture will be delayed. That was one observation. And we could see in case of the bending strength was improved in case of reinforced PETG only at a layer thickness of 0.1 mm with maximum of 25% at 70% infill percentage for full honeycomb. So that was about flexural strength, which improved. And these were some of the conclusions, major conclusions of this work, that the carbon fiber actually improved the tensile strength at the layer thickness of 0.1, and also it improved the bending strength by reinforcing it with carbon. Another work which was related to tribology of FDM printed parts, wherein we did some surface texturing. Surface texturing has a very great potential in improving the tribological performance, because texturing actually interrupts the local depressions as well as it acts as they trap the wear debris. Because if the wear debris comes between two sliding surfaces, their third body abrasion happens and it causes abrasive wear, and that actually causes ploughing, which is very detrimental for the material. And they also act as reservoirs for lubricants. So if we add, if we are doing a wet lubricated, condition, then in these textures, the lubricant gets stored, and that actually reduces the heat generation from friction and then leads to less wear. So surface texture, since it requires a lot of intricate, work, and it is a little bit difficult by conventional processes, but fused deposition modeling technique can achieve it by, very finely it can be done by this FDM, and we have did it in our lab. We actually selected 3 different textures on the basis of previous literature, and then varied the texture depth and the texture diameter for the different samples, and then we tested it for the coefficient of friction at dry conditions, and we could see that texture, T2 is performing good, and you can see here also that at all loads, we checked it for different loads, and texture T2 proved to be better in comparison to other 2. And likewise, for lubricated condition, we could see that texture T3 is performing better, and we could see from the frictional characteristic also that with the increase in the number of cycles, or when we with time, what is happening, that the curves or the frictional characteristic is getting smoother, and not much deviation or erratic behavior was observed, which is actually good, because these textures or these depressions basically store 2 things. One is the lubricant, another is the worn out material, which helps in improving the tribological performance, and which actually delays the wear process, and which is a good thing. And so another observation was the percentage reduction in coefficient of friction for different textures. So if you see at low speeds and at high speeds, we could see a good amount of percentage reduction, which is around you can see around 70% percentage reduction, which is a good thing. So this work is already published. You can read it, and we did some SEM analysis of these worn textures at a particular load, and we could see that very peculiar, worn surface features were observed, and smoother. We could see in comparison to non-textured samples, we could actually improve the wear behavior, and very different and very peculiar worn surface features were observed because of the entrapment of the wear debris, and because of the storage of the lubricant in these small textured holes, or you can say these depressions. So these were some of the conclusions from this study. That coefficient of friction is minimum for T2 for under dry conditions, and while as for lubricated conditions, T3 was the better one. But this was actually observed that it is because of the synergetic effect of 2 factors: the real contact of area and the lubricant retention capability of the textures. So that was the key, I would say, observation. And as I told you, that plowing of the material in bulk was absent, which is because of effective layer formation and entrapment of the wear debris in the depressions of these textures. So you could see that reduction of coefficient of friction was observed for texture T3 for lower speeds, while as for T1 at higher speeds, it was observed that it is giving us maximum reduction in coefficient of friction. So that was these were some of the conclusions which we could draw from this study. Another work which we did was, again, it was a stage 2 of those PETG's work, which we first tested for mechanical strength. Then we did tribological tests on these PETG and carbon fiber reinforced PETG samples. we actually tested the samples at five different loads, 10, 20, so on up to 50, and both at high speed as well as low speed. And the wear track diameter and the sliding distance were kept around 100 and 1500. And then so as to check the morphology of these worn surfaces, we did SEM analysis. And you could see this is a typical tribometer in which this is a counterface disc. This is the pin holder in which we place the pin of the material which is to be tested. There is a transducer attached, which actually stores or which actually senses the frictional force, and the output from this transducer goes to a computer, and then we get a computer generated in a software, we get the value of coefficient of friction. And just here we can apply the loads. There is a pulley out here which is not visible, I think. So that actually applies the load between the counterface disc and this pin material. This counterface rotates, and rotation of this counterface disc actually helps in the sliding action of these two materials. So this is a pin on disc, and it is a unidirectional, I would say, pin on disc tribometer. It is not a reciprocating one. It is a unidirectional sliding wear tester, which we used in this study. And we could see, because carbon fiber primarily, if some of you must be knowing that carbon fiber, like graphite, is a very good solid lubricant. Carbon, because of its layered structure, actually because of its sharing of its consecutive layers, is bonded by weak van der Waals forces. And when we use it as in case of lubrication, it acts as a solid lubricant. And that was visible here, that when we tested these samples, the coefficient of friction reduced, and at different loads, this was visible, that in comparison to non-reinforced PETG, the coefficient of friction is lowered. That is one. And if you see at a higher RPM also, a similar behavior was observed, that the carbon fiber has a good role in reducing the coefficient of friction. From the frictional characteristics, we could observe that for PETG, if you run it for a large number of cycles, the trend is that with the increase in the sliding distance, or with the increase in the number of cycles, the coefficient of friction is increasing, and which is not actually a good trend. But when we reinforce it by carbon fiber, the coefficient of friction is showing that when we increase the number of cycles up to, say, for example, 2000 or to 2500, the coefficient of friction is going down, which is actually due to the layer formation capability of carbon and the solid lubrication capacity of carbon, which is playing a role, and which is actually helping in exhibiting this behavior. From the worn surface analysis, we could see that carbon fiber reinforcement is actually helping in reducing the I would say wear. Particularly smoother grooves were observed in case of carbon fiber reinforced this PETG. And we could see that no heavy plastic deformation, no those plowing marks are not visible in case of the carbon fiber reinforced PETG, and which is actually in confirmation to the coefficient of friction results which we are getting, because of the tribofilm formation capability of carbon. This is actually happening. So we could conclude from this study that COF, that the coefficient of friction is reduced because of carbon fiber addition at all loads and speeds. And this is happening because of the intrinsic lubricating nature of carbon and the film formation capability of carbon. And we could see from the SEM analysis that that these different fracture modes and different these wear modes are observed, and smoothing of the worn surfaces actually happens by addition of carbon. We have done some work related to development of exoskeleton for
Hello. Yes, there is some internet connectivity problem, and the speaker will join within 2 minutes. Please
Okay,
wait.
sir. Okay.
He will join within 2 minutes.
Okay, sir.
I'm sorry for the interruption. It was a power failure.
Okay, no issue, sir. Okay, sir. Please carry on.
Wait a minute. Is the slide visible now?
Yes, sir. Visible.
So we were here, actually. We were here that we have done some work on project on this exoskeleton for fracture, development of this exoskeleton, and we all have encountered, or someone in our family has encountered fractures, particularly during in our childhood, wherein we had to actually there are two common fractures which actually happen. One is a Colles fracture, another is a Montiago fracture. So Montiago fracture actually affects both bones of the forearm, and it is usually a fracture in the ulna, and the top head of the radius is dislocated. This is very serious, and which actually sometimes requires urgent care. And we all know that we use those plaster of Paris or a very heavy, exoskeleton so as to help it to recover, and which was actually non-water resistant, extremely heavy and cumbersome to carry, very poor in air ventilation, resulting in allergic skin reactions and dullness of skin. And it actually causes irritation due to accumulation of sweat. Imagine you have to go for a meeting tomorrow, and you have this with you, God forbid, and you feel very, very irritated, or in a very humid conditions you are working, and then your skin may get irritated and may actually develop some dermatological issue also. So what were the objectives of this small project? To design an exoskeleton bracket and fabricate this by using 3D printing technique. And then we did some feedback and testing from some experts, patients, and doctors. You could see this exoskeleton bracket, which we developed for avoiding compartment syndrome. And what we could observe is that mobility of the proximal and the dextral joints to avoid muscle atrophy due to its lightweight, and the range of motion. What actually happens is that in addition to the the bone, it actually, the conventional one seizes the movement of your muscles, which is not actually good. So here we could see we could give proper ventilation for air so that it does not sweat, and it was light to weight. We developed some 2 to 3 designs, and then we developed a questionnaire based upon level of comfort, ease of joint movement, air circulation, muscle support, aesthetics, locking mechanisms, susceptibility to shocks, and some 50 to 60 reviewers. We have a hospital here nearby of our university. We did some interactions with patients and doctors there, and then we could see that the weightage to each parameter was given, and then we ranked our designs. So this was one work which was actually used for a small product development, and this is work in progress. We are actually improving the design part of this. Another work was, which I have not shown here, was related to development of impellers by 3D printing, and we did some testing in case of submersible pumps, and particularly in case of your water coolers, which we use at home. I have a case study. Suppose we all have some experience of air travel, and we use that buckle, steel buckle, while the air hostess or the air staff tells us to buckle your seat belts. And you could see that if a conventional seat buckle weighs, this is Airbus 380 project in which they have developed an optimized design, and a conventional seat buckle actually weighs 155 grams. And if you design it by titanium and make an optimized design, it boils down to 70 grams, which is actually a reduction of 55%. So weight should be reduced. That means for an Airbus 380 with an economy seating of 853 seats. For one flight, this would mean a reduction of 72.5 kg. If you see over the airplane's lifetime, 3.3 million liters of fuel would be saved. Or in other words, 2 million euros could be saved, assuming that a saving of 45,000 liters per kg an airplane lifetime. So you can see from this small example how a small change in design will actually help in number one, saving millions and millions of rupees and improving I would say, the design for environment feature of your product. So that is where 3D printing will actually help. We are in a very now we are coming out of this COVID, but if you see post-COVID or during COVID also, 3D printing had a role to play, from development of masks to face shields to ventilator parts, wherein we did a interactive, I would say, I had a small role in that, wherein so we developed valves which like this. It was an open source project, and a single ventilator in an emergency situation could be used for 2 patients. Due to lockdown and other things, transportation of these parts was difficult. But if you have a 3D printer, you can develop these small things for these emergency situations at your place, and with minimum human intervention. If you see the 3D printing market, what I see or foresee is that 3D printing will now pick up, particularly in case of healthcare. And since governments as well as industries are now feeling that healthcare needs to be improved, and there would be much interest of researchers also. So the healthcare 3D printing market is bound to improve, and this is one area which can be explored from research point of view also. So we did some, study on how medical equipment in COVID could be developed by, 3D printing. So reverse engineering, it can help in reverse engineering and developing critical parts, wherein say, for example, a condition of lockdown is there, or your critical medical equipment is down, your spare parts have to come from very far away country or some foreign country. But if you have the CAD files and other, you can develop some, I would say, interim arrangement till your actual part is actually delivered. So a lot of opportunities, and in this area. So the takeaway points from this talk would be, I think, that 3D printing is a disruptive and affordable technology which entrepreneurs and designers can use in prototyping, development of small parts, and reverse engineering. There is a huge opportunity for the next generation to bring ideas, products, and solutions to life. A lot of opportunities for researchers, particularly from developing nations. As I told you, like we don't have the state-of-the-art laboratory infrastructure, but 3D printing, we can innovate and exploit the 3D printing potential, particularly this polymeric one, and do some good work in this area. Then designers, rather than outsourcing, can start using this technology for day-to-day activities. And mechanical behavior of 3D printed parts can be tailored, and studying the effect of various 3D printing process parameters on mechanical strength is important. Complex designs and lightweight parts can be developed by 3D printing. And 3D printing has a potential use in surface texturing. And studying the friction and wear behavior of 3D printing parts is an important research area and needs to be explored in detail. This work was a joint work by our group and particularly the students. I would like to mention them. Atharva Mega is the supplier of our 3D printing lab, and Sai Labs, Patiala, SMVDU Narayana Hospital, and Medical Aid Center, because some part of the work was done in collaboration with them. If you, these are the papers which actually I presented here. They are all available online. If you want to study in detail about the kind of work which we have done, these are available in these 5 papers. The first one is in Journal of Materials Engineering Performance, another in Polymer Testing, and third one in Research on Biomedical Engineering. You can just search it if you want to carry out further research in this area. And that was all from my side. We will have a question answer session. And if you want to contact me, collaborate with me, or need some help from me, you're always welcome. This is my working number and this is my email ID. You can contact me. We are very open to collaborations. We also want people who are working in the same area to collaborate with us, to look for joint research proposals, to do some good projects together. So that was all from my side. Now, if you have any questions, you are welcome.
Okay. Thank you very much, sir. Participants, please, if you have any query, you can ask to sir. Please, you can unmute your mic. Yes, participant, please. You can unmute your mic for the questions, chat. Otherwise, you can type your questions in the chat box also. No query?
There are only 2 conclusions which I can draw. Either everything
Sir, your voice is not clearly audible. There is a little bit, I think, lack in the voice.
Is it audible?
Yeah.
Now?
Right now
Yeah. I mean to say that since there are no queries, the 2 conclusions can be drawn. Either they understood everything, or I was able to, share in a good way, or the other way around. So
no, sir.
Let me be positive, and I'll conclude the first one.
Actually, sir, we can consider your first one, that everybody understand everything. I think so.
Yeah.
So thank you very much, sir, Irfan sir, for being with us and making this program successful. Thanks a lot. And the future,
thank you.
Definitely.
I thank you and Professor Garg and other colleagues from your university for giving me an opportunity. It is always a pleasure to talk to fellow colleagues and fellow faculty members who are working in other in universities, particularly post-COVID. We don't have much interaction beyond our lab, beyond our department. So
Right,
that is how we grow. We want to collaborate, and we want to meet people, make new friends, make new connections, so that we grow. And nowadays, it is not possible to work in a lab and do research like earlier people used to do. That without collaborating, you cannot move, because now the kind of research people are doing and the kind of facilities and kind of interdisciplinarity which is coming. So what we need is to work together, and then only we can grow as a nation and as a society. So
Right.
I thank you with my folded hands, Professor Garg, and you and other colleagues. So thank you. I wish the other colleagues also a grand success to this program. So that was all from my side. Shall I log out or?
Yeah, thank you very much. Actually, sir, Gert sir, right now he's in a meeting with our vice chancellor, sir. So it's a urgent. That's why he is not.
No issues. Convey my thanks and regards to sir and all other participants. So
thanks a lot, sir. Definitely, sir. We look forward for our upcoming FDPs in our university. So definitely, we'll look forward for that. You also. So we are thankful to you, sir.
Thank you.
Thank you very much, sir. Thank you.
We will share something about functionally graded parts because we are doing a project on that. So we will have a different perspective next time.
Right, sir.
So
thanks a lot, sir. Thank you.
Thank you.
So yes, participants, there is a little break of 30 minutes. We can join again at 11:30. So please, till now we have a short break of half an hour. So we'll again meet at 11:30 because our next session that is on metrological assessment of additive manufacturing by Professor Harish Kumar, NIT Delhi. So please have a short break and we'll meet again at 11:30. Thank you very much.
दिया
Welcome back, participants. We are just waiting for our sorry. We are just waiting for our speaker. So as soon as he joined, we'll start this session. Yeah, very good morning and welcome back again. So it's a great pleasure for me to introduce our next session speaker, who is going to talk us about a key issue in 3D printing, that is metrological assessment of 3D printed parts. Thank you, Professor Kumar, for being with us today for making this event successful. Dr. Harish Kumar, he is an assistant professor, Department of Mechanical Engineering, NIT Delhi. He is a BTech from Guru Gobind Singh Indraprasth University in 2003. He has completed his PhD in 2015 from Guru Gobind Singh Indraprasth University. He was a senior scientist E1 at CSIR National Physical Laboratory in New Delhi from 2014 to 2017. He was scientist C in CSIR National Physical Laboratory from 2010 to 2014, and he was a junior scientist at CSIR National Physical Laboratory in New Delhi from 2007 to 2010. He has more than 50 research publications in SCI and Scopus publications. So we welcome you, sir. Please, over to you, sir.
Thank you, sir, and thanks for generous introduction. I am thankful to the organizers, Professor Garg, Department of Mechanical Engineering of DCRUST Muthan, for giving me an opportunity to discuss very key issue of additive manufacturing. So, should
sir, your voice is a little bit not clearly audible, sir. Can you raise?
Hello?
Yeah.
Hello, now it is clear, sir?
You can, sir, can you raise your voice by your system?
Yes, sir, I have raised to maximum now. Now it is clear, sir?
Okay, sir, no problem, sir.
No. Thank you, sir.
Okay,
thanks
sir.
a lot for giving me an opportunity to discuss here with very key issue of additive manufacturing. So I am thankful to the organizers. So should I start now, sir?
Please, over to you, sir. Carry on, sir, please.
Thank you, sir. Thank you.
Please, sir, share your screen.
Yes, sir. I'm just. Is screen visible now?
Yes, sir, it is visible.
Yes, sir. I'm starting just in a few seconds, please.
Okay, sir, no problem.
Is my screen visible, sir? That PPT?
Yes, sir, clearly visible.
Okay, sir. Thank you. So, the title of the talk is Metrological Assessment of 3D Printed Parts. So, as we are aware, 3D printing. We are discussing 3D printing for a very long time. Now it is not a new technology. If we go to the history of 3D printing, we should go back to around 1990. 3D printing is like printing. So if I try to compare it with conventional printing, for example, you are having a paper, you want to take a print over it. So what are you doing actually? You are impressing certain characters through that black, colored, whatsoever your cartridge is there over the paper. And we are not able to ascertain what is the height of the characters which is printing over the paper. Certainly they may be nanos actually, and even below the nanos, but your ink is finished after some time. So it means those characters are basically impressed over paper. The same concept is here in 3D printing. What is the difference in paper printing and 3D printing? Here you are able to see what is printed in a three-dimensional form. And whatever you are printing on your paper, the dimension of the character, means height especially, is so small that we don't consider it as a 3D printing. Clear? So additive manufacturing and 3D printing, whatever we call, both are just alternately used for each other. So I am Harish Kumar from National Institute of Technology, Delhi, former senior scientist, National Physical Laboratory, Delhi. So would like to discuss a new area, metrological assessment of additive manufactured parts. So this presentation attempts to take over the following areas: additive manufacturing, what it is, a basic classification of additive manufacturing, role of additive manufacturing, metrology in additive manufacturing, selective laser magnetic, materials and methods, resultant discussion, and future scope. So this work basically is quite new. If you will see, only a very limited work has been reported in this area. And this work I am doing with my one former colleague at National Physical Laboratory with my PhD scholar. So in this area, you would if you will see very limited papers, especially from Richard Leach from University of Nottingham, will be available. And even I'm sure he has not implemented that ISO guidelines for measurement uncertainty evaluation so far for a 3D printed parts. So quite new area. I'm very much hopeful participants will be benefited and will be motivated to do some state-of-art work in this very narrow domain. So additive manufacturing. Additive manufacturing, as the name indicates, that it is the manufacturing which is additive in nature, while our conventional manufacturing is subtractive in nature. So I am not going in much detail of additive manufacturing because now even school kids are studying what is 3D printing. So AM makes objects from a digital model by depositing the constituent materials in a layer by layer manner using digitally controlled and operated material slaying tools. So a digital model of an object which can vary from a pizza slice to an aeroplane wing, for example, because if you will see the YouTube, you can get easily videos how BMW is able to make some prototype of 3D printed cars. The car which are even transparent. You can see how your engine is working. This is the beauty of 3D printing. So materials that are consolidated from the smallest particle, for example, liquid droplets, wire, powder, etc. A tool for laying materials, generally it is extruding tools or a laser source. A digital control system for the tool to lay the material by layer to build the shape. of the object. So basically there are two manufacturing, as we discussed, subtractive manufacturing and additive manufacturing. In subtractive manufacturing, your block is, you can see, for example, it is a shape of a cube, and then you are getting the some shape which you want to. So you are removing the material with the help of a machining process, getting your final product, and this is your waste product. So additive manufacturing is basically a zero loss manufacturing process in which we are having some starting material, like in a form of wire, in a form of powder, in a form of liquid droplet. Then we are having certain nozzle or laser source. Then we are making layer by layer, and you are getting certain final product with as minimal as waste. So the aim of the 3D printing is basically zero loss fabrication process. So that is the main idea behind additive manufacturing. Of course, it is not zero loss, because here you are making the object layer by layer. So after finishing process, you have certain waste material, but the quantum of the waste material is too less in comparison of the subtractive manufacturing. So what are the different steps of additive manufacturing? If you are really willing to discuss additive manufacturing, so in additive manufacturing, you are starting with your material selection. So your materials may be ferrous, non-ferrous, etc. It may be fiber or plastics, depending upon your printer, whether you are working with fused filament fabrication or FDM printers, if you are working with polyjets printers, and if you are working with metal printers. So the main criteria in deciding your material selection, it is the mechanical properties, your shape, size, flowability, and what kind of application you're looking for. Now, how your process selection? Your process selection depends upon whether it is powder bed fusion, whether it is binder jet technology, or direct energy deposition in case of selective laser sintering. Like design selection, what you are looking for, your support for the structure, geometrical consideration, 3D CAD model. So basically, additive manufacturing is digital manufacturing. You are not looking for if you look for CNC machining actually. So what are you doing? You are first deciding what is your geometry of the object. Clear? So here also you are expected to have a 3D CAD model of your object. So similarly, layout selection like chamber filling, orientation, form, fit, function, etc. And then post-processing. Post-processing in conventional process, we look for machining, heat treatment, short pinning, polishing, and painting, etc. The similar kind of post-processing are also there in additive manufacturing to make your product as a practically viable and aesthetically driven project. So what are the critical areas of additive manufacturing? First, mechanical properties, optimized energy and materials, dimensional accuracy, precise product, and surface quality. So these are certain areas which are to be addressed or while taking into consideration if you are going through the additive manufacturing and you have chosen additive manufacturing as a route to fabricate the desired product. So for just a very brief discussion to the participants, I am discussing classification of additive manufacturing as per ASTM category. So according to ASTM category, your first category is wet photopolymerization. We know that stereolithography comes under this category. Here it is a liquid based process mainly useful for polymers, as well as you may infuse some ceramics to them. Benefits, you can fabricate large parts, excellent accuracy, excellent surface finish and details. Drawbacks, limited to photopolymers only, expensive, precursors or slow building process. The main global players in this is 3D Systems and NY Zinetech, Germany. Similarly, powder bed fusion. Powder bed fusion is basically selective laser sintering or melting, SLS or SLM, or in which we involves electron beam melting. Powder based processes, the starting phase material may be powder based. It is a powder based process, so you may have polymers, metals, ceramics, hybrids, etc. Benefit, large range of material options, powder bed acts as an integral support structure. Clear. So what are the drawbacks? Lack of the structural integrity, high power required, size limitation. Basically, our metal printers come into this category, SLS or SLM. So 3DS, EOS, Blueprint, Renshaw, HP, etc. are now global players in this area. Similarly, material extrusion. Material extrusion is basically fused filament fabrication, which we generally call as FDM also, fused deposition modeling. So here we are having layer by layer. So we are either taking solid wires or liquid. If we are taking solid wires, then we are heating up to them some temperature, and we are converting them into a semi-liquid state. So neither it is completely liquid nor it is solid, so that it can be laid in form of layer by layer. So generally it is useful for polymers and composites, and it is easy to handle, very friendly process for very friendly prototyping. So the main drawbacks are poor surface finish, vertically anisotropic, and if you will see, there are certain mark force stresses, and 3ds are some of the players in this area. So similarly, sheet lamination, binder jet, direct energy deposition, material jetting, etc. These are also certain different techniques. But in this our present study, our focus is on SLM. So, how additive manufacturing is useful in different areas? So these are certain areas you can see. For example, lattice structure, aerospace parts, automotive parts, biomedical or knee implants, and cranio-maxillofacial skull implants. Sometime back, if you could remind, around 2 years back, there was a news in the newspaper that a dog in Canada, more precisely Ontario City, he got a brain tumor. So basically, the tumor was in his skull. So his skull was to be removed. So if you are removing the skull of a dog, then certainly he was going to die. But the doctor said they were not willing, they were not able to tolerate if dog is dying. So with the help of 3D metal printing, they prepared a skull of titanium alloy for him, and then his tumor was removed and the same was covered with the skull, which was fabricated with the help of 3D printing. So what I mean to say, 3D printing has been useful in different areas. So I have just given you some areas where metal additive manufacturing has been used. Additive manufacturing process is yet to be matured. And if you will see, most of the work which are done on additive manufacturing, they are basically for prototyping. So some people call it only useful for rapid prototyping. But of course, a lot of people are working in different areas. So these areas were just to show where additive manufacturing is metal additive manufacturing is useful. So metrology in AM. This is a very critical area. So what is metrology? Can anyone explain? Can anyone explain what is metrology? Any participant who would like to tell? What is metrology? Can anyone explain? आप में से किसी पार्टिसिपेंट का गाना चालू हो गया, प्लीज बंद कर दो.
Participants, please mute yourself.
If anyone is willing to explain what is metrology, then it's good. Otherwise, I will explain.
Participants, please mute yourselves.
Yes, metrology is basically science of measurement. Now, we people, especially in industry and academics, just a minute, sir. Just a minute. Hello. Hanji.
Metallurgy is scientific study of materials.
मैं इसीलिए फोन काट रहा हूँ, मैं लेक्चर में हूँ. अरे सर मैंने किसी को ब्लॉक नहीं किया, मैं अभी क्लास में हूँ.
Metallurgy is scientific study of materials.
No. We are talking metrology. Metrology is science of measurement. So
Yes. Metallurgy is science of measurement. Definitely.
Metrology.
Yes, sir. Yes.
So in metrology, what we are doing, we are taking repeated measurement. So the question is there, why repeated measurements are required? Why? For example, you are doing some experiment for first time. You got certain value. Can you rely that whatever values you are getting is correct? Of course, it may be correct, but it may be incorrect also. So you are going to take repeated measurements to evaluate whether there is deviation or not. If I'm talking as a layman, but generally you will see whenever we are doing certain experiment, we are taking observations generally once. So that is not a good practice. So what is the intention of studying metrology in any kind of process? It means you are basically repeating the experiment or repeating the measurement. Clear? So if you look for metrology in any kind of process, our main intention is to ensure the quality control of the process. For example, if I'm discussing additive manufacturing, so it means I am discussing the quality control of additive manufacturing. So here in additive manufacturing, what is my product? The specimen which I am fabricating. So if I am fabricating some specimen, then my main intention is to see whether the dimensions, whether the properties, whatsoever, my listed criteria are within limits for the given products or not. For example, here, shape deviation is one of the most noticeable effect while most of the additive manufacturing process. Now you will ask me a question, sir, if you are so worried about metrological capabilities of additive manufacturing, then why we are working over additive manufacturing? Clear? In your conventional manufacturing process, or we call subtractive manufacturing, your material removal rate is too much. And some of the process, some of the shape which I cannot fabricate with the conventional process. So what is my main target? What is my main target here? To develop a practical viable solution with no compromise over the quality of the product by involving metrology in that particular process. For example, you are fabricating a cylinder. Clear? your cylinder is having certain diameter, certain height. Your cylinder is of 10 centimeter, 10 millimeter dia and 20 millimeter height. The same you have fabricated with the help of additive manufacturing. So if I have to use this cylinder somewhere, then the dimensions of this cylinder should be plus minus some tolerance so that it can fit easily. If it is beyond the tolerance, either less or more, so if it is smaller, then it will not get so fit easily, and if it is more than the nominal size after tolerance, then it will not be of so use for me. For example, you see your your NA parts. So here in this case, so metrology plays a very important role. How? Clear. We discuss. We have utilized selective laser melting process. This is a DMP Flex 350 SLM bed based printer. We use this printer available in Mumbai. And this is a selective schematic process of SLM process. I'm not going to discuss in detail. So basically there is a powder bed or powder recoater. Here is a build plate. So here we are getting controlled laser beam and we are getting object built here as per the design process. So SLM is a powder bed fusion based metal AM process where input material are used in a powder. So in our present process, we have used SS316L, which is a austenite steel with low grade of carbon. Why we took it for its excellent corrosion resistance property and biocompatibility, and it is very useful in aerospace, construction, and implants and surgical equipment, etc. This is its set. So, what was my main motive? We are willing to characterize this material with the help of 3D printing. So for example, if I am willing to study its tensile properties, then I will have to prepare tensile specimen as per ASTM standard. If I'm looking for wear properties, I will prepare a wear specimen according to its wear that standard ASTM G99. If I'm willing to study fatigue properties, then we will prepare the specimen as per for fatigue guideline. So dimensional characterization is the first and foremost important criteria to make an assessment of any part. So in this study, what we have done, we have fabricated some wear specimen according to ASTM G99 for 3D metal printer. And we have varied some of the process variables like laser power, scan speed, hatch spacing. Your laser power has been varied from 250 watt to 350 watt, 250 watt, 300 watt and 350 watt. Scan speed is 700 millimeter per second, 900 millimeter per second, 1100 millimeter per second. The hatch spacing is 80 micron, 90 micron and 100 micron. These are some of the space means parameter and their level values which have been taken with the help of some past research. So we have adopted a L9 orthogonal array according to the Taguchi design of experiment, and we designed these 9 experiments, and each experiment has resulted in 5 specimens. So there are 9 experiments, 1, 2, 3, 4, and each one is 5 times. So in overall, there are 45 specimens were fabricated. As we discussed, we were not focusing that only one specimen is the correct one. So we overall fabricated 5 specimens for single experiment, and total 9 experiments are there. So overall 45 experiments were conducted. means 45 specimens were prepared. So it is a typical wear specimen. You can see its height is 30 mm, diameter is 8 mm. Clear? So these are specimen 1, 2, 3, 4, 5, 6, 7, 8, 9. So you can see. So these specimens are fabricated, and now my targeted dimensions are 30 mm is the height and 8 mm is the diameter, and this semi-sphere at here. Should I trust these dimensions as it is? No. So what we have done, we have used a coordinate measuring machine available at National Physical Laboratory, Delhi, for dimensional characterization of the wear specimen for their diameter, for their height and cylindricity. Resolution of the CMM is 0.1 micron. Probe diameter is 3 mm. Uncertainty of CMM is 1.8 plus L by 100 microns. Thermal coefficient of expansion of specimen is there. Deviation in the temperature is 20 plus minus 2. Controlled environment you are working, and relative humidity is controlled within 50 plus minus 10% of RH, relative humidity. So these are certain setups of CMM. These are the some specification. So now what we are doing, our main intention is to measure the dimensions of diameter, height and cylindricity for this wear specimen, and to measure the uncertainty of measurement in all the cases. If uncertainty of measurement is very high, we can even take a decision that these specimens are not acceptable at all. If uncertainty of measurement is small and deviation to the nominal dimensions is small, then we can make a decision that specimens are acceptable. So uncertainty of measurement has to be made like a tool for making a decision for acceptance and rejection. Industries need to practice the uncertainty of measurement to enhance the quality of measurement as well as better knowledge about the results, to meet the desired tolerance specifications, to report on the calibration certification, and to reduce risk and improve credibility of the test results. So this is the flow diagram for conventional method for measurement of uncertainty evaluation. So these are the specimens 9. So this is the average value of 5 specimen for specimen 1, 2, 3, 4, 5 like this. So uncertainty in diameter, uncertainty in cylindricity, and uncertainty in height. So you will see different process variables, because every specimen means every 1, 2, 3, these are of independent experiment. You will see everyone is different. Clear? So for example, your specimen 1 has uncertainty in diameter. This diameter is 8.2, 8.02, while your cylindricity, for example, its cylindricity is in 0.04 mm, while its uncertainty in height is 33.55. Clear? Plus minus something. So you see every specimen has its different uncertainty in diameter, different uncertainty in cylindricity, and different uncertainty in height. So accordingly, you can make a judgment. While your height should have been 34 mm, but in none of the case you got 34 mm. Your diameter was supposed to be 8 mm, but your diameter is varying from 7.98 mm to 8.08 mm. 0.1 mm variation is too much. Too much. If we discuss as a metrologist point of view, 0.1 mm means 1000 100 microns. So 100 microns is a very big value if we are thinking as a metrologist point of view. Clear? So similarly, our cylindricity, ideally it should have been 0.04, but you will see its value is something different, not everywhere same. So I mean to say, you will see, ideally all specimens should have the same value, but you will see there is variation. It means your process is not as consistent as it has been claiming. If you will see any 3D printer, no 3D printer will discuss about the metrological capabilities. They will discuss, yes, it is very good. They will discuss about the resolution, but they will not discuss about the measurement uncertainty or uncertainty of measurement. As a mechanical engineer, as a product designer, as a fabricator, we must know the relevance of measurement uncertainty. So you will see for diameter, our overall expanded uncertainty has come 2.2 microns, cylindricity 2.68 microns, and for height, it has come 2.74. So it shows that the laser power has been more significant effect than scan speed and H spacing. High laser power may result in splashing during the power melting process, which is dangerous. High laser power results into larger melt pools. So we should work with low laser power, but if you are taking laser power very less, then it will take more time, and moreover, your material may not be melt suitably. So similarly, hatch spacing is responsible for inaccuracy in the part. When you will see it is varies from 0.08 mm to 0.1 mm. Uncertainty of measurement is more because increase in hatch speed decreases the melt pool dimension. Low scan speed, the laser material interaction time is high, so the powder particle get enough time. Although there is less deviation in samples when compared to their nominal values, which shows SLM is a good accuracy, but still I believe difference of 0.1 mm is not very small. So what are the future scope of the presented work? So uncertainty of the components depends upon some other factors also, like model assumption, numerical approximations, unknown simulation parameters, and measurement errors in the calibration. To reduce the measurement uncertainty, deep understanding and improvements of either in process, in situ control, post-control methodology, etc. required. Uncertainty of AM process related to design, manufacturing, materials and post-process should be explored, and parameters like scanning strategy and orientation should be explored to develop more understanding of physical metallurgy of SLM process. So this study is now further expanded by us. We are now trying to correlate this uncertainty of measurement with the mechanical properties of the specimens fabricated. We are trying to explore some mathematical relationship supported by experimental observations that whether there is any direct or indirect relationship between uncertainty of measurement to the projected mechanical properties. For example, this is the wear specimen. We got different specimens with different measurement uncertainty. Whether this measurement uncertainty is having significant impact over the wear properties of that specimen. So such kind of challenging work need to be explored, because other 3D printing is like a normal facility. You can do whatever you wish, but as a researcher, as a technocrat, we must try to focus over such areas where we are able to develop some relationship between the between the parameters and their projected values. So this is very important. I don't know whether how much up to what extent I was able to convey my information to the participants, but I believe this is a quite new approach where we are trying to establish some importance of the metrological process for additive manufactured parts. So quite a new area which we should try to explore to implement to develop a relationship between the stakeholders, means like process, properties, etc. So very important. And now if anyone is having any question, then I will be very happy to answer, because this is the area where I should expect a number of questions. Any question, please?
Yes, participants, do you have any query? Please, you can ask. You can unmute yourself. Yes, please. No query. Yes, participants, please, if you have any query. There is one chat, I think, science of measurements. No, thank you, sir. So thank you very much, sir.
Thank you. Thanks
for your enlightened talk. Thanks a lot for being with us and making this program a successful. Thanks a lot, sir.
Thank you, sir. Have a good day.
Thank you very much, sir. Thank you. So next session. So yes, participants, so we have a break and the next section will start at 2:30. So please join at 2:30 sharp. Thank you very much.